Thank you. Okay, so our first speaker is Thomas Tauris. Thomas is a professor of theoretical astrophysics at Aalborg University in Denmark, and he works on many aspects of compact objects, in particular type binaries and their formation, evolution, and interactions. Thomas just finished 7 years of work on a new textbook, Physics of Binary Star Evolution, from Stars to X-ray Binaries in Gravitational Wave Sources, together with a colleague from University of Amsterdam, which might be of interest of some of you here. He obtained his PhD in '97 based on radio pulsars observed in Australia, and he was a Marie Curie Fellow at University of Amsterdam from '97 to 2000. Then Nordita Fellow and assistant professor at the University of Copenhagen. In 2010, he moved to Germany, where he worked for 8 years at the University of Bonn and the Max Planck Institute for Radio Astronomy. And in 2018, he returned to Denmark as a full professor at Aarhus University before moving to Aalborg University in 2022. So thank you, Thomas. Your floor is all yours.
Okay, thank you very much for this kind invitation. Can you hear me well?
Yes, it's fine.
Okay, thank you. Great. Yes, thank you very much. I gave my last head seminar when I visited Harvard in 2015, so it's about 8 years ago. I gave a seminar on formation of millisecond pulsars, and I really enjoyed that, and I hope to return to Harvard once I get the opportunity. So today I'm going to talk about ultra-stripped supernovae and their evolutionary context. So most massive stars are born in binary systems. Actually, close to 100% of all massive stars are born in binary systems, and through a long sequence of interactions with mass transfer, supernova explosions, etc. Some of these binaries might survive all these stages of evolution to the final stage until we have a pair of compact objects, 2 neutron stars or black holes, or one of each, which will eventually merge and give rise to a gravitational wave source. We have a lot of evidence for this evolution along these tracks, so it's not just all hypothetical wishful thinking of a theoretician, because we do have observations all the way from the CRH main sequence of very massive binary stars. And of course, after the first supernova explosion in such a binary, we may be able to observe a radio pulsar, which is orbiting a massive star. Now, shortly thereafter, these systems are observable as high-mass X-ray binaries due to the dense stellar winds of these companion stars. And once the massive star fills its rush lobe, it gives rise to dynamically unstable mass transfer. The system evolves into a common envelope. And once the hydrogen-rich material has been peeled off the donor star, another phase of mass transfer will be initiated, which I'll talk about today, the so-called case BB mass transfer. And in this process, the outer layers of this donor star is being completely stripped. And this is why we have dubbed these supernovae that occur second, ultra-stripped supernovae. So that will be the topic of today. If the system survives this second supernova as well, we'll end up with typically 2 neutron stars, which will then be observable in radio pulsars, but also with LISA up to 1 million years before they actually merge, if we're talking about a galactic system. And of course, once these systems merge, they give rise to gravitational waves. So we actually believe that all gravitational wave mergers containing neutron stars, which developed from an isolated binary system, they have all experienced this ultra-stripped supernova when the second core collapse happened. If you're interested in more details of these typical calculations, here's an example here, including the masses of the stars, orbital periods and ages, and so forth. And there are some references down here where you can see more details about the formation of, for instance, double neutron star systems. So as I mentioned, I'll be focusing on these last mass transfer stages, case BB rod slope overflow until the second core collapse. So what I'm focusing on now is the part of the evolution where we imagine that the hydrogen-rich envelope of this helium star has been lost in a common envelope. The common envelope shrinks the binary system, so now we have a very tight binary system with an orbital period of typically a few days or less. And this helium star will then start evolving. And once the helium star initiates helium burning in the shell, the star will expand and give rise to another phase of mass transfer, so-called case BB mass transfer. And this can happen in many binary systems where the accretor can be either a black hole, a neutron star, or a massive oxygen and magnesium white dwarf. And this case BB mass transfer has two important effects. So first of all, the neutron star, let's assume it's a neutron star from now on, accretes material, and this process, it will be spun up to rapid spinning. And secondly, the donor star will be stripped off all these outer layers of helium, which will leave behind more or less a naked metal core by the time of the core collapse. And this is the reason that these supernovae are called ultra-stripped supernova explosions. So we started to model these systems in detail about 10 years ago. And here's an example of a plot showing the mass transfer rate from the helium star as a function of time. The typical duration of this X-ray stage is of the order of 10 to 50,000 years. It depends on the orbital period of the binary system. The wider the orbital period is, the more evolved is the donor star when it initiates the mass transfer, and therefore the shorter is the subsequent mass transfer timescale. So we see timescales of about 10,000 years if the orbit is about 2 days. These are calculations where the donor star is a 3 solar mass donor star, and the accreting neutron star has a mass of 1.35 solar masses. But you can see the extent of the X-ray phase increases the shorter the initial orbital period is. So one thing that's really interesting, and what actually triggered all these observations, is the recycling of the firstborn neutron star. So if one has a detailed binary still evolution code, we get information about the mass transfer rate as a function of time. And when we have that, then we can work out the torque acting on the neutron star, since the magnetosphere of the neutron star truncates the inner edge of the accretion disk, and then we can work out the torque acting on the neutron star. So from these calculations, we can work out the amount of mass transfer that the neutron star needs to accrete in order to spin it up to a certain equilibrium spin period. And this is a very, very steep function. So if we consider the firstborn neutron star in a double neutron star system, these pulsars have typically spin periods between 20 and 100 milliseconds. So we only need to accrete of the order of 1,000th of the solar mass to achieve that. But if you want to have a 2 millisecond pulsar, you can see from this little table down here in the corner, you need to accrete 100 times more. You need to accrete about 0.1 solar mass. So this is very much in line, these theoretical calculations, with what is actually being observed when we look at pulsars in binary systems with either neutron star, massive white dwarf, or a low mass white dwarf companions. And these systems come from X-ray binaries, which are either low mass, intermediate mass, and high mass X-ray binaries. And we can actually quite well understand why these three different kinds of binary pulsars are grouped into different systems with different spin periods. The double neutron star systems experience a very rapid mass transfer phase, so they have only slow spin periods, whereas the millisecond pulsars with spin periods of 2 or 3 milliseconds, they come from the low mass X-ray binaries. But I can go into more details about this if you're interested. So back to these ultra-stripped supernovae. What you see here to the left is an example of the first calculations in 2013. What you see is a so-called Kippenham plot of a 2.9 solar mass helium star that transfers material to the neutron star. So you can see right after the termination of core helium burning, when the donor star undergoes shell helium burning, the star expands, it fills its rush lobe, and on a very short time scale, the outer helium-rich layer is being peeled off, and we end up with a naked metal core with just a very, very tiny layer of helium just before core collapse. So this is actually a process that we discovered on our computers, and we modeled these supernovae thereafter, and we modeled these ultra-stripped supernovae because they have ejector masses of only of the order of 0.1 solar masses. You can see these envelopes here are really, really tiny. So later, these calculations were refined. There were other groups working on the light curves and the spectra of these ultra-stripped supernovae, and there's been done some modeling of 3D explosions of these, led by Bernhard Müller, for instance. So the definition of an ultra-stripped supernova is that it is a supernova where the amount of ejector mass is less than about 0.2 solar masses. And furthermore, the companion to the exploding star must be a compact object. Otherwise, you will not achieve this extreme stripping prior to the core collapse. So actually, it was very interesting when we did these calculations in 2013, just before we were submitting our paper. We noticed this very interesting discovery from one of your colleagues at that time at the CFA, Maria Drought. And she discovered this supernova 2005 EK, shown right here. And in this plot here, you see the light curve, so the absolute magnitude in blue as a function of time since the explosion. And her observations are shown here with black dots. And we realized we could actually explain this light curve from one of these ultra-stripped supernovae. So this was a really neat way to explain these relatively weak but very rapidly decaying light curves. Just to illustrate again how extreme these stars are by the time they collapse, you can see here cross sections of these stars from our models as a function of the final core mass. So you can see it is indeed a more or less naked metal core with just a tiny layer of carbon and helium on top. So that's why, again, we call these ultra-stripped supernovae. And because of the tiny ejector mass, these ultra-stripped supernovae will often, but not always, but they will often give rise to relatively small supernova kicks. Now, since the wonderful discovery of Maria Drought and collaborators in 2013, there's been quite a number of other candidates for these ultra-stripped supernovae. In particular, there's some very interesting ones marked here in boldface from the Caltech supernova group. So you can look up these papers if you're interested in the observational evidence for these supernovae. Here you can see one of them here shown in this plot to the right. So my surprise, I saw a paper being published 2 months ago about an X-ray binary where the authors claimed that this is was an ultra-stripped supernova, but I can assure you that this is certainly not an ultra-stripped supernova for many, many reasons. And I have no idea why this or how this paper was actually being published in any journal. It's very easy to show. I have bachelor students who have modeled this system, and you can easily show that you could have ejector masses up to 2 or 3 solar masses of material. So there's no way this is an ultra-stripped supernova. So just to show a few more slides about the properties of these ultra-stripped supernovae. With respect to spectral types, whether or not we see this ultra-stripped supernova as a type 1b or type 1c, of course, depends on the amount of helium which is left in the envelope by the time of the supernova explosion. So here you see, based on our initial helium star masses before the mass transfer, you can then see the amount of helium which is left in some of our models, depending on different initial orbital periods. And also, these ultra-stripped supernovae can be core collapse, which is due to either electron capture or due to ion core collapse. So if the metal core is around 1.4 solar masses, you are within a tiny window where the core collapse can actually be electron capture rather than an iron core collapse supernova. So we also did some very simple calculations about the rise time and the decay time of these light curves, and you can see more details in our 2015 paper. So I'll just skip that and move on to some modeling. So Bernhard Müller has taken on the task of modeling some of our models. He has exploded these cores in the 3 dimensions using hydrodynamical simulations. And the reason was we were very curious to figure out what is the kick velocity imparted on the neutron star. And you can see marked in green here, there are 2 cases shown here where the neutron star had a mass of 1.28 solar masses, and it achieved only 11 kilometers per second as a kick velocity. Whereas another of our models here led to a more massive neutron star, and it received 238 kilometers per second. So whereas there's a general trend that these ultrastrip supernovae often give rise to small kick velocity, it's not always the case. And this is also what we expect, because a system like the Hulse-Taylor pulsar with the 2 neutron stars actually has a relatively high proper motion and therefore a large recoil due to the supernova explosion. So it must have received quite a kick. And this fits actually quite well as long as the neutron star, which is more massive, the more massive neutron stars are more likely to receive large kicks. So if you're interested in probabilities of these supernovae, it's relevant because this is the second supernova explosion. What is shown here is the probability of these double neutron star systems to remain bound after the supernova explosion. And you can see, because you can see here, you need a rather large kick velocity of several hundred kilometers per second to actually avoid the system to remain bound. If the kick is less than a few hundred kilometers per second, they're very likely to remain bound, in particular if the binary system is quite tight, of course. If you're interested in the effects of ultrastrip supernovae, the shell ejection in tight double neutron star systems, and X-ray emission from fallback material, you can look up this paper by Kashiyama et al. From last year. Or if you're interested in long-term radio curves of ultrastrip supernova remnants, there's another paper here from last year by Matsuoka and collaborators. So let me just briefly say that 2 years ago, we published the first full calculation where we succeeded to calculate these systems all the way from the CRH-mate sequence of the helium star until the onset of the core collapse itself. And you can see this donor star, in this case, a 3.2 solar mass donor star, evolved all the way to iron core collapse. Just last month, we published our first of these calculations for a black hole neutron star system, and you can look up this paper if you're interested in this. This, of course, has quite some relevance for gravitational wave sources. So finally, for those of you who are interested in the spins of black holes from these double black hole mergers, I made recently some work trying to model the distribution of effective spins, and I concluded that I can actually model the distribution very well if I allow for the tossing of the spin axis of the black hole when it formed in a core collapse. So if you have this interest, I would suggest that you might want to look up this paper. I think the results are actually really interesting. So finally, as was mentioned in the introduction, I spent 7 years writing a new textbook on the physics of binary star evolution. So it covers the evolution of binary systems, X-ray binaries, low and high X-ray binaries, formation of millisecond pulses, and gravitational wave sources. So in case you need a new textbook or you're just interested in the topic, this book was just published last month as an electronic book, and it comes out in paper here in about 2 months' time from now. It's 864 pages. There are many, many figures and equations. There are more than 80 student exercises, and it's completely up to date with the latest LIGO data, including observing 1.3 and many new interesting X-ray and pulsar discoveries. So my final slide is just to say there some amazing synergies between stars and supernovae, compact objects, X-ray binaries, and gravitational waves. Thank you very much for your attention.
I have a question.
Sure.
Can I have this book as a specimen copy? I will pay later on, but if you can please provide the specimen copy of this book, I will be highly thankful to you, sir.
Sorry, I did not hear that very well. Could you please repeat this?
My humble request to you that actually I need this book, Physics of Binary Star Evolution. And I'm very thankful if you provide me the specimen copy, if you have. So can you forward me the specimen copy, please?
I don't have a copy of the book myself yet.
Okay.
It's coming out in June, and I haven't not even received the book myself. I just have a stack of papers, of printed papers, but I don't even have the book myself yet. But it should arrive anytime now.
Okay. So is there any opportunity so one can get this book in a because I'm Indian student, Indian researcher, and Indian student, so I'm very much eager to take this book. So is there any reduced?
Yeah, you can. As I mentioned, if you go to follow this web page, I included a link here in the PDF file. I think our host today can distribute the PDF file, or you can just find it on the Princeton University Press. You can actually now, you can already get the ebook, so you can get the electronic version of the book right now.
Oh, okay. Thank you so much. Thanks a lot.
Thank you. So I don't think we have any more questions from the online audience. Do we have any questions from, let me turn on the video here so we can see, from the in-person public here? Does anyone have? Well, we can share the link for the ebook after the.
Yeah, sure. It's in the PDF file that I distributed up right here.
Yeah, we can share with the other CFA scientists. So if no one else has any questions, let's thank Thomas again. Thank you.
Thank you very much. My pleasure.
And we also shared his email. If anyone wants to schedule a meeting with him, you should contact him via email, please. Thank you.
Sure.
So thank you now, just get my. Okay. So our second speaker, it's let me see here. Yes. So our second speaker is Nhut. Can you share your screen with us, please?
Sure.
Just check. Okay. So Nhut is currently he's serving as an assistant research scientist at NASA Goddard, where he's working within the CRISM team. Prior to that, he was a postdoc researcher at Max Planck Institute for Astronomy, and he obtained his PhD from University of Rome in 2016 under the supervision of Professor Pasquale Mazzotta. His research aimed to exploit state-of-the-art cosmological simulations to study the effects of supermassive black hole feedback on hot gaseous atmospheres ranging from hot ISM, CGM to ICM. His works primarily focus on modeling synthetic X-ray observations of simulated galaxies and clusters of galaxies in order to make comparison and interpretation existing in forthcoming X-ray observations. So recently he's actively involved in the development, the Line Emission Mapper Mission, and he co-lead the CGM Science Working Group. So, Nhut, go ahead. The floor is yours.
Thank you. Yeah, thank you a lot for giving me the opportunity to talk at the seminar. Yeah, I'm kind of shifting the gear a little bit to talk about the process at the larger scale, at the CGM scale. So the topic I would like to talk with you today is about the effect of supermassive black hole feedback and how it may have effect on the CGM and how we can broadly expect with a future X-ray emission called Line Emission Mappers, a mission that I know many of you at CFA have been actively involved in. So this is a theoretical forecasting studies, mainly based on cosmological simulations. So I would like to acknowledge my main collaborators, including Annalisa Belevich and Dylan Nielsen in Heidelberg, Agos Borten, Gary Schellenberger at CFA, as well as the member of the LAM CGM working group. So I would like to begin by saying that there is a consensus among current cosmological simulations that AGN feedback or supermassive feedback is the fundamental ingredient in modeling galaxy formation and evolution. So without AGN feedback, simulation would be struggling in reproducing galactic galaxies, in which they would produce too many overmassive galaxies, which is apparently not suggested by observations. So in the current model of galaxy simulation, the black hole physics is often captured in terms of the so-called effective subgrid models. And basically, these subgrid models just contain three main components that treat different aspects of black hole physics, including black hole seeding, black hole roll, and black hole feedback. And the current status is that current simulations employ very different effective subgrid model for the black hole physics, especially when it comes to how to do the black hole feedback. Simulations are really different from one to each other on the way how the black hole may inject the feedback energy into the surrounding areas. So despite on those different details in the subgrid recipe, phenomenologically, current simulation predict quite similar, qualitatively similar effect of supermassive black hole feedback on larger scale, like on the CGM scales. And actually, there are two main effects of that. So the first one is called ejective effect, which refer to the feedback ability in evacuating a large amount of gas out of the central region of the galaxies. By this way, the feedback would strongly impact the gas constant, metallicity, as well as the kinematics of the CGMs. The second effect is called preventative or hidden effect. So it just simply refers to the fact that the feedback can also heat up the gas within and around the galaxies. And of course, by this way, the feedback would mainly impact the CGM temperatures, entropy, and ion abundances. So it should be noted that the two effects here could couple to each other. For example, the ejective effect, when it increases the kinetic energy of the gas, some of the kinetic energy can be also converted into the thermal energy, thereby increasing the CGM temperature as well. So observationally, the detection of those effects remain very elusive, partly due to the reason that our observation of the CGM is still very limited. For example, if you take China or SM Newton, we can only probe the X-ray emission that come from the very central region of the galaxies, maybe up to a few tens of kiloparsecs. So at larger radii, the CGM signal would be completely dominated by the fallout, the Milky Way fallout, which is simply the emission of the CGM in our own galaxies. So on the other hand, if you look at the current simulations, like in illustrated TNG, it's predicted that the black hole effect should exist at much larger scale, at hundreds kiloparsec scale. So in this regard, you see this would be crucial for us to observe the CGM at much larger scale so that we can fully capture the effect of the black hole feedback. So in this context, I introduced the Line Emission Mapper, or LEM in short. So as CFA is one of the member of the leadership team, so I guess you may have heard about this mission on many occasions at CFA. If you don't, please check on Woodruff. So in short, LAMP is a mission concept that aim to propose for the NASA astrophysics probes missions. And it is currently designed to be a X-ray integral unit with microcalorimeter on board and with large field of view. So the current design of LAMP make it an ideal instrument for roving physics of the sea gems for a couple of reasons. So the first thing we noticed that is with microcalorimeter on board, LAMP would have advanced spectral resolution at the level 1 or 2 eV. So with this high spectral resolution, LAMP would be able to resolve individual in metal light in the X-ray surface. So whereby being able to separating the CGM signal from in the external galaxy from the Milky Way far out, simply thanks to the redshifting of the lines. So this is some kind of thing that is impossible to be done with the current CCD-based instruments. The second thing is that with the last field of view, LAMP would be able to probe the CGM at the very last radii. And this is crucial for our study of the CGM in the nearby galaxies. So yes, so being motivated by this recent development from the observational side, we carry out a forecasting study for LAMP. So in this study, we make use of the different data sets taken from different simulation projects, including the TNG, Eagle, and Simba. So we provide the predictions from those simulations. Especially, we focus on some observable consequences of the black hole effect on the sea gems. And finally, we also discussed about the possibilities how to probe the effects with LAMP via observation of light emissions. So the very first result we noticed is that the current simulations, the 3 considered simulations here, produce remarkable diversity when it comes to CGM properties. For example, here I'm showing the surface brightness map in Oxygen 8 that's produced by the 3 simulations. And here I show the map for the entire simulated box, which is about 100 megapixels per site. So you can see by eyes that the large scale distribution of the Oxygen 8 is very different from simulation to simulations, especially for the case of Simba, in which we can see that its Oxygen 8 distribution is much more extended compared to the other 2 simulations. When we go to smaller scales, like at the CGM scale, we see the diversity even stronger. For example, here I'm showing the radial profile of the Oxygen 8 again for the 3 simulations, and this profile is for a sample of Milky Way-like galaxies. And so you can see that the 3 simulations produce well-separated profile at this mass range. And if we look at the gas properties, such as the gas density, temperature, and metallicity, that are produced by the 3 simulations. So we notice that the diversity in the light emission that we see here just simply reflecting the diversity in the gas content between the 3 simulations. For simulation like Simba, is produced significantly less gas content compared to like TNG or Eagle. But the 3 simulations do share one thing in common. That is the way how they quench star formation in massive galaxies. So if we look at the gas density profile for star forming galaxies and compare those profiles with the quiescent counterpart, what we noticed is that the 3 simulations predicted that the star forming galaxy contains significantly higher gas content compared to the quiescent counterpart. But at the same time, they have like lower temperatures, lower gas temperatures. So this result just suggested that in those 3 simulations, the star formation quenching is mainly done via the gas explosion. At the same time, the gas is also heat up so that it can prevent future star formations. And this gas explosion is driven by the black hole feedback. So one way to see it is if we look at again the gas density and how it changes with the mass of the central supermassive black holes. We notice that for galaxies that host more massive black holes, which means that the black hole inject more accumulated feedback energy over their lifetime. So those galaxies with more massive black hole, they tend to contain less gas content compared to those galaxies, with lower black hole mass. So this just simply suggests that the gas explosion is mainly driven by the black hole feedback. So this way of quenching star formation that is predicted by the simulations has an interesting observable consequence. So if we look at the light emission, for example, here option 7 forbidden light in the 3 simulations. So what we notice that there's some kind of dichotomy between the star forming and the quiescent galaxies, in which the star forming galaxies appear to be significantly more X-ray luminous compared to the quiescent counterparts. And this is predicted by on the 3 simulations. And it's not only for one line like here, but also for other lines like option 8, Iron 17, and also other lines. So what we do notice that the dichotomy, the degree of this dichotomy is different from simulation to simulation, but the qualitative trend is similar among the 3 simulations. It's just simply because this dichotomy is the reflection of the ejective effect of supermassive black hole feedback. And in those simulations, this feedback effect is a quenching mechanism. So the question, how can we probe this effect with LAMP? So now I'm coming back again to the point that LAMP would have advanced mapping capability. So it would be comfortable to probe this effect simply by observing the light emission, just mapping the light emission map of the CGMs. So for illustration here, I'm showing the surface brightness map in option 7 forbidden line for a sample of quiescent galaxy taken from TNG. And if we compare to the surface brightness map of star forming galaxy at the same mass range, so you can see even by eyes that the 2 populations have very different surface brightness map, in which star forming galaxies appear to be not only more luminous in option 7, but it's also more concentrated. So by this way, LAMP can probe this ejective effect of the black hole feedback. Okay, so now I move on to discuss the second effect of the black hole feedback, which is about the hidden effect. So if we look at in detail how the feedback operates in individual galaxies, so what we notice is that, for example, here I'm showing the case for TNG simulations. We notice that the black hole feedback can launch large-scale outflow, and the outflow in turn can strongly impact the gas thermodynamic properties of the gas above and below the disk, in the way that the outflow expels the gas out of the center regions. It heats up the gas along the way, it drives the gas velocity, and at the same time, it also enriches the gas along the way. So all of the actions, we noted that they all happen preferentially along the minor axis or in bipolar directions. So this kind of orientation or direction could be explained simply due to the fact that when the outflow expands outwards, the galactic disk redirect the outflow in the direction that it experiences the least resistance, so which is in the bipolar direction. So motivated by that feature, so we carry out an exercise in which we examine how the light emission of the CGM may depend on the azimuthal angles. So what I'm showing here is the surface brightness profile for a sample of TNG galaxy at Milky Way mass range, and in which I compare the profile that taken along the minor axis to the one that taken along the major axis. And to quantify the difference between the two, I use the minor to major ratios, in which a value like close to unit mean there's no difference between the two directions, or the emissions are more or less isotropic. And I did exercise for different energy lines from low to high energy. So what we noticed here is for the case of TNG is that when we go to higher energy lines, like in option A, I-17 or neon 10, we start to see that the minor to major ratio increases. And if we look at the case for SMBH, the trend here is more or less similar, although it suffered much more scatter compared to TNG. And finally, for the case of Eagle, so we still more or less see the trend there, although in Eagle is predict much less anisotropic signal, or less different between the profile that along the minor to major axis. But anyway, the trend is still there. So we see that at the population level, all the three simulations predicted that the emission of high energy lines is more enhanced along the minor axis. And this is simply the reflection of the hidden effect of supermassive black hole feedback that I just discussed earlier. And because this effect happened preferentially along the minor axis, so that's why we start to see the enhancement of the emission in high energy lines along the minor axis. So this is the effect at population level. But it does have some interesting implication for LAMP if we use LAMP to observe, the CGM emission in individual galaxies. For example, here I'm showing again the surface brightness map for one galaxy at the Milky Way mass range taken from TNG simulation. Is oriented edge-on. And if you look at this map at increasingly higher energy lines, like you start to see some interesting features. Like if we look at the map at high energy lines, for example, in I-17, we start to see that the emission of the CM start to be more anisotropic, in which is more concentrated along the minor axis. Yes, not only that, we start to see some kind of X-ray bubbles, which is similar to the Eurostar bubble that we observe in our own Milky Way. But this is for an external galaxies. So in other words, so the X-ray bubble here is just simply the manifestation of the anisotropic signal that we seen earlier in the high energy metal lines. So in other words, because the black hole feedback drive the anisotropic signal in the temperatures, and this kind of anisotropic signal can be manifested into the X-ray bubbles that I'm showing you. So the final point that I would like to make is that so because this is the temperature effect, so we can use the light ratio, for example, the ratio between like oxygen 8 to oxygen 7 for forbidden light, which could be considered as a good proxy for the temperature. So if we observe the galaxy in this light ratio, we also can observe the X-ray bubble, similar to the case that when we observe in the high energy light years. And not only that, if we use that light ratio and then derive the temperatures based on, like, for example, APEC model, so we notice that the temperature that derives by on those light ratio can give us a very good proxy for the emission weighted temperatures of the CGM. So this way is very promising for us to probe the thermal structure of the CGM, which is something impossible with the current instruments. So I guess then that's all I want to tell you for today. And for the take-home messages, I think my talk is mainly centered around the questions, how the supermassive black hole feedback that affect the host CGMs. And for this current cosmological simulation predict that there are two main effects of black hole feedback that's caused on the CGMs: the ejective effect and the preventative or hidden effect. Those two effects can have some observable consequences that we can observe on the CMs, which is the first one, dichotomy between star forming and quiescent galaxy in line emissions. And the second one is the azimuthal dependence of the line emissions. And I also show you that, with the future X-ray emission like LAMS, we would be able to probe the effect just simply mapping the CGM in narrow band. So thank you for your attention.
Thank you. Do we have any questions from the audience? Let me just check. I don't think so. Yes, go ahead.
So in modeling on the larger scale, the people doing that modeling now and dealing with the development of galaxies, they tend to just put in the feedback effect by hand, right? They just say, well, we'll just deposit some energy into the middle of our proto-galaxies and we'll put it into the baryons and, it'll do the right thing. So do you have any more detailed suggestions for them based on these results? I mean, it's kind of a...
So yes, you're right. So for the three simulations that I'm studying here, like TNG, EGO, and SMBH, the injection scale of black hole feedback is about kiloparsec or sub-kiloparsecs. So, but the effect that I'm talking mainly here is at a much larger scale, at least 10 kiloparsecs or 100 kiloparsecs. So I think so. If we just simply observe the CGM, what suggestion we can give to people who do modeling is that, whether their model is too efficient in expelling the gas or too efficient in heating up the gas. But I don't think that by observing the CGM, we can give them the suggestion on which scale they should inject, because anyway, it's much smaller than the CGM scale.
Mm-hmm.
Do we have any more questions from the audience? Well, thank you then, Nhut. As I said before, if you want to set up a meeting with him, just email him. I think Federico sent his email along with the announcement for this seminar, but you can just ask us again. So thank you again for the talks today. It was amazing. Thank you.
Thank you. Goodbye.